Hello everyone, today let's solve the problem number 190, reverse bits. So what the question states here, we are given a 32-bit unsigned integer as input. So here you can clearly see we are given a 32-bit unsigned integer. So this is the binary representation of this number 43261596, whatever they have given here. This number, this is the binary representation of it, right? So here this unsigned integer, we are converting this one to the binary number n equals this one they have given here, right? This one, right? So what we have to do here is we have to reverse its bits. Again I'm telling, we have to reverse its bits and we have to return the resulting unsigned integer. Reverse it, in short, we just have to reverse its bits and return the resulting unsigned integer. That's what they have given in the question. So here after reversing the bits and we have to return the unsigned integer, right? This is the unsigned integer. So whenever we reverse the bits, we will get the solution this one, right? So this one, when we convert back to the decimal or the unsigned integer here, we get the value this one, 96417619, whatever they have given, right? So that's what we need to return as output. I hope this is clear. First thing is they have given unsigned 32-bit integer, this one. So we need to convert this one to the binary and then we have to reverse its bit and return the unsigned integer again. So that's what we need to do here in this case, right? So I hope this is clear. Same goes with the example 2 as well. You can just go through the example 2. You will understand this one clearly, right? I insist you to go through the example 2 as well, right? So this is fine. I hope the question is clear what we need to do and what the question states, right? So I hope the question is completely clear. Next, what we will do here, first let's discuss the approach, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written, right? So first we will discuss the approach. So let's discuss the approach step by step here. The first step here is we will be going with the bit manipulation, right? So we'll be going with the bit manipulation approach, right? So this one we have to keep in mind. I have considered the same first example that they have given in the question so that it will be easier to understand, right? So let's discuss our thought process and what we'll be doing, and finally how can we articulate that one in the form of code after discussing all the edge cases, right? So let's discuss everything step by step. First thing here, we will reverse the bits of a 32-bit unsigned integer using the bitwise operations. Just keep this in mind as we are going with the bit manipulation. We will reverse the bits of a 32-bit unsigned integer using the bitwise operations, right? So just give me a second, what happened here? So this is fine, just give me a second here. So first step here is we will initialize result to 0. We will consider result variable, extra result variable. So we will consider initialize result to 0. Why we are initializing the result to 0? Because we have to store the reverse bit somewhere. That is the reason we'll be considering result variable, and we will be initializing the result variable to 0. I hope this is clear. And we will be looping 32 times. Since there are 32 bits, we are dealing with a 32 bits unsigned integer, right? So we are looping 32 times since there are 32 bits, right? So in each iteration, what we will do, we will shift the result left by 1 bit. This we will see in the iteration step by step. I'll not be showing 32 iterations, but I'll be showing you 3 or 4 iterations so that it will be enough to understand. So what we will be doing, so here in this case, in each iteration, shift result left by 1 bit. Here result 1, right? So next step here is extract the last bit of n using n end 1. We'll be making use of the end here. So extract the last bit of n using n and 1. So we are extracting the last bit. This one keep in mind, this is important. We are extracting the last bit of n here on the second step using n ampersand 1 or n and 1, right? And operator. So here this one we will append it to the result using bitwise OR. So we'll be making use of the bitwise OR here. What we'll be doing after the second step, we will be appending it to the result using the bitwise OR here. This symbol basically, if you are not seeing this one OR symbol, right? Bitwise OR. So finally, the fourth step is within the second step. This is we will shift n right by 1 bit. You can clearly see here this one, right shift, right? So we will shift n right by 1 bit, right? Here you can clearly see this one equals 1. This is fine. The third step or the fourth step here is after 32 iteration, result holds the reversed bits. Return result as an unsigned integer. Here unsigned integer we have clearly shown here, this one, right, shift operator, right? So this one we are returning result as unsigned integer. So these are the steps that we'll be going through, right? So this is the approach that we'll be going through. Let's consider the example 1 and see the same thing. Here you can clearly see we are considering the step-by-step bit transformation here. This is the iteration, first iteration, second iteration, third iteration, and this is nothing but I can't show all the 32 iterations. It will be huge. So first 3 iterations we are just right shifting here, right? So bit. So you can clearly see here 1, 2, 3, 4, 5, 6, 7. So 7 zeros initially we have. So here we have 8 zeros and 1. The final bit will go here. 1110. This will go. And in the third iteration we have 9 zeros here, followed by here instead of 1110, 0 will go and 111 last here, right? So this one n binary, n ampersand 1 we have already considered here. N and 1, why we will be using n and 1 here, you can clearly see in this one, I think second step I had explained, I think, yeah. Extract the last bit of n using n and 1 and operator, right? Here that's what we are doing here. We'll be going with 0 here, since this is 0. Here also this is 0, last digit 0. Here the last digit is 1. You can clearly see here this is 0, this is 0, here this is 1. So we have considered 1. Here 32nd iteration it is 0. Again we are considering 0 here in this case. We are extracting the last this one, whatever here, extract the last bit of n using n and 1, right? Now when we do n and 1, so the resulting binary we get here is this one for 1, for 2, for the third iteration, and for the 32nd iteration we get the reversed bit, right? So this one, when we convert, we have to convert it to the decimal finally, right? So we have to convert it to the decimal finally. So after converting we get the output this one, 964176192. so this is the output that we get, which is equivalent to the output that they have mentioned in the example 1 in the question, right? So 964176192. so this is equivalent to the solution that they have given in the this one, but output example 1, right? Output. So the approach works absolutely correct in this case. So here this is the approach that we'll be going with. So just keep this in mind, right? Next step is here. I hope the approach is completely clear. Now let's discuss the edge cases one by one here, right? So let's discuss all the edge cases one by one here. In this case, the first edge case that we will be going with here is all bits are 0. So here we'll be going with all bits are 0 in this case. Output will be 0 in this case. So output will be 0 in this case. Reversing all zeros still results in 0 itself. So while we reverse all the zeros, it results in 0 itself. So output will be 0, right? So this is for the condition all bits are 0. The second edge case that we'll be going with here is all bits are 1. We have considered all ones here, right? So the output will be in this case. So just give me a second, what happened here? So this will be 4294967295. So I can just try out in the same way that I showed for the example 1 in the approach. You will get the output, this output, right? You will get this one as output, right? So reversing all ones still results in this number, particular number, right? So I hope this is clear. This is for the condition all bits are 1. So let's move on with the third edge case. Only one bit set at MSB. MSB is nothing but most significant bit. Here you can clearly see only one bit set at MSB. So the output will result in here. Let me give here all zeros here. 3, 4, 5. Just give me a second here. This will be 1 here in this case. So this is fine. This is 1 in this case. So output will be this one. This is for the condition only one bit set at MSB, or the most significant bit. So the single one bit moves to the least significant bit. Here this moves from here to this one, the final one. So you can clearly see here we have 1 here, right? So as output, the single one bit moves at the LSB. nothing but least significant bit here in this case, right? So the final one, let's move on with the final edge case or the fourth edge case here. Only one bit set at least significant bit. Only one bit set at LSB, least significant bit. Input here, this one. So here 1 we have. So the output will be here 1. So here the output will be this one, 32-bit integer, right? So here the single 1 bit moves to the MSB or most significant bit in this case. Here you can clearly see this one, right? So here this one we have, this one we have. So this is fine. So only one bit set at LSB. This is for the condition, only one bit set at LSB. You can clearly see here. So the single 1 bit moves to MSB or the most significant bit here. This is fine. So this is for the condition, only one bit set at LSB. So these are the 4 edge cases that we need to keep in mind here. The first edge case was for all bits are 0. The second edge case was for all bits are 1. The third edge case was for only one bit set at MSB. And the fourth edge case was for only one bit set at LSB. Right? I hope this is completely clear. Next, let's start writing the code. Here, let's start writing the code here. The first thing is, we have discussed this one. We will initialize the result to 0 and we will initialize the integer or I to 32 here. We are considering 32-bit unsigned integer, right? So let's go with the while loop here. While I minus minus. So while I minus minus means we are looping 32 times here, right? Since we have a 32-bit integer, we will be looping 32 times. So I will consider simple while loop here. Next step here is we will shift the result left and add the last bit of n. So I can just give here result equals result left shift operator, this one 1 or n ampersand 1 here. This one is fine. So let me do one thing. Yeah, this is fine. So we are just shifting the result left and we are adding the last bit of n here in this case. This is simple to understand, right? So finally, we have discussed this one already as well. So we will shift n right by 1, nothing but unsigned shift to handle the unsigned integer. This one we have discussed this one in the second step, I think. Second step, I think, I don't know exactly in the approach. Second step we discussed this one. So this one I can just write this one on this, right? So we are just shifting n right by 1, right? So we are just handling the unsigned shift to handle the unsigned integer in this case. So the final step here is we have to convert the binary to the unsigned integer before returning. That's what we need to do. So if you remember, triple right shift operator 3 times and 0 we gave, right? So that one, that's what we will return here in this case. The result, this one, we are just converting to unsigned integer before returning, right? So we need this one in the integer format, right? So not in the binary format. So here you can clearly see, right? So this is fine. I hope the code that we have written is completely clear. Now let me hit the run button. Let's see. I hope this works. So you can clearly see here the sample test cases are getting passed here. Means the code works correctly. Let's see whether it works for all the test cases or not. So here you can clearly see all the test cases are getting passed. So the code works absolutely correct in this case. So let's quickly discuss the complexities for the code that we have written. So here the approach that we went with here is bit manipulation. We know that one. We have already discussed this one. So what would be the time complexity here? So the overall time complexity would be big of 1 in this case. So why it is big of 1 here? Because it always runs for 32 iterations. So it always runs for 32 iterations. We have directly considered I equals 32 and we are making use of while loop, right? It always runs for 32 iterations. Since it always runs for 32 iterations, the overall time complexity would be big of 1. So what would be the space complexity here? The overall space complexity would be big of 1 as well, because it only uses few variables. In this case, we are making use of result and I. That's it, right? So which doesn't require any extra space here. This requires only constant space. It uses only few variables, right? So overall space complexity is big of 1 as well. So the time complexity and the space complexity for the code that we have written is big of 1, right? So I hope the solution or the code that we have written is completely clear as well. For now, this is it. Thanks for watching, guys.